Welcome, everyone. Thank you so much for joining us today. Our webinar is entitled Introducing Genova's Innovative Methylation Panel, Discussion on Clinical Utility and Case Review. Our speaker is Dr. Michael Chapman. My name is Dr. Lenore Powell. I'm a medical education specialist in Genova's Atlanta branch, and I will serve today as your moderator for the webinar. We would like to welcome Dr. Michael Chapman. Dr. Chapman is a licensed naturopathic physician who graduated from Bastyr University in Seattle, Washington. Upon graduation, he spent 3 years in private practice before joining the team at Genova Diagnostics. His areas of clinical focus are hormone regulation, GI health, and autonomic balance. Prior to medical school, Dr. Chapman earned his Bachelor of Science degree from Indiana University with a focus in neuropsychology. He later worked as a microbiologist, performing pharmaceutical research on cancer cell lines.
Thank you, everyone, first and foremost, for being here. As Lenore mentioned, we're going to be discussing Genova's new methylation panel, and we've received a lot of excitement, a lot of interest so far, and a lot of questions. So, got a ton of information to cover today. I think one of my jobs is going to be to make sure that I'm not talking too fast to get everything crammed in there. So, let's, without further ado, kind of march along and kind of work on discovering how to incorporate methylation testing, evaluation, and treatment into your clinical practice. So, like any good presentation, we want to start with the learning objectives, review one carbon metabolism. I'm going to talk a little bit about it, but pretty briefly, because there's also another video available on our website where we kind of go into the basics of one carbon metabolism, but we'll review that a little bit and then spend the bulk of our time discussing the new methylation panel and how to apply nutrition lifestyle therapies to evaluate and treat methylation imbalance. So, we use this term methylation quite a bit in our sort of functional and integrative space. And I think it's good to start with taking a step back and just kind of really thinking about, well, what is methylation? And at its core, methylation is something as simple as transferring a single carbon from one molecule to another molecule. And this is why methylation is also referred to in the literature as one carbon metabolism. And it looks like this. You have a molecule, S-adenosyl methionine, or SAM. This is also what's available as a therapeutic known as SAMe for supplementation, and it has this extra carbon. And what happens here is that carbon can be used in a whole host of reactions, and this is just one example. Converting 4-hydroxyestradiol into 4-methoxyestradiol. And why is this important, right? This is done by the enzyme COMT, and 4-hydroxyestradiol we know as a phase 1 metabolite of estrogen, which if it's not metabolized appropriately through phase 2, it can turn into an oxidative stressor. It can form what's called quinones that are DNA addicts, cause DNA damage. So this is just one example of methylation at work. And after SAM donates that carbon, then it's left without that carbon and forms a molecule called S-adenosyl homocysteine, or SAW. And this is really what's happening when we talk about methylation. This is it at its core. And it's not just for detoxification that we use methylation. For example, turning arginine into creatine is a huge methylation burden on the body. I've heard estimates somewhere around 30% of all methylation reactions is involved in the formation of creatine. So you can see how important it is there. Also in metabolizing our neurotransmitters, like turning norepinephrine into epinephrine, another important function of methylation. But, when you think about what we just looked at, what makes this particular enzymatic reaction any more or less important? It kind of looks like a lot of the enzymatic reactions that we see from biochemistry class. And I think a good answer to that is, if you want to know how important a single process is to a system, you just need to look at how often that process is used within the system. So it's really not that the methylation reaction is all that special, but rather how many processes depend on methylation is really kind of the take home. So then what systems do depend on methylation? Well, we mentioned creatine production, DNA and RNA synthesis, epigenetic gene regulation, hormone regulation and detoxification, as we saw in that first example, energy production, cell membrane repair, lipid metabolism, sort of the list goes on, right? So there's a ton of systems that ultimately depend on methylation. But even taking a step back from that, at its core, methylation is about cellular aging, because we're talking about the ability for the cell to maintain DNA, the ability for the cell to make glutathione, which reduces free radical damage to that DNA. So, I even sometimes we'll have patients come in and say, well, what are you talking about methylation and why should I test for it? Then I might kind of go and say, there's a lot of interest in the anti-aging movement. It's all coming back to, we look at cell function and we look at GI function, but underneath all that, methylation is a critical process that ensures all these things are happening at the right time. And the research indicates that as well. One quote that I pulled out here saying, especially nutrition-based decisions, including intake of essential nutrients, are involved in the metabolism of methyl groups. And as such, the continuous maintenance of a proper one-carbon metabolism may be important for healthy aging and may slow the development of age-related pathologies in general, right? So that's a pretty powerful statement to support why methylation testing is important and why it's important to consider in our clinical evaluation. And where does it fit into all of our kind of picture of evaluation and treatment? Here ultimately we're talking about this bottom left quadrant, which is the lifestyle determines the functional disturbance, and that's going to arise before symptom manifestation. So if we're really talking about preventative medicine, then this bottom left sliver is, I think, where we also want to be focusing our treatment and our evaluation. It only makes sense. So with that kind of brief overview, let's kind of get into why we're all here and discuss the methylation panel, how to interpret it, what it looks like, what to do with it clinically. And broadly, 4 pages here consist of a first page report overview, giving you a quick report of findings, a biomarker page, a pathway page, and then the genomic results. And we'll go into these in a little bit more detail here. So with this first page, at the top we have these 3 pillars, and then we kind of have an overall evaluation for methylation status. And so put together, this is kind of an interpretation at a glance. And already you can see right away that this is a comprehensive systems biology assessment, right? It's not just a genotypic marker test. It's not just a phenotypic marker test. And by that I mean we're combining genes along with the actual biomarkers. And really, this is a first of its kind approach. It's the first time that a test is looking at putting together both the genomic results with the biomarkers to get a more well-rounded assessment. So here on the first page, you see these 3 pillars, and we have them categorized as methylation, the SNPs, and then transsulfuration. And just broadly, when I think about seeing a lot of biomarkers in that first pillar under methylation, I would be considering some methylation support. If I see a lot of things showing up under that transsulfuration pillar, I'd be thinking about antioxidant support, and we'll certainly go into that in more detail. Then we have the methylation panel genomics. We're looking at 10 different SNPs. This is an add-on, and we're looking at things like MTHFR, COMT, but also some more novel SNPs like MTRR, MAT1, SHMT1. And if you're not familiar with these, hopefully by the end of the hour you will be, because we'll be kind of going into these. Also keep in mind that SNPs can result in either an upregulation or a downregulation of that particular enzyme. So if there's a positive that you see there, you want to make sure and kind of take a look at the top of the section and remember, oh, this is going to make that enzyme work slower, or this is going to make that enzyme work faster. The second page is where we have all the individual biomarkers listed out, starting with the functional ratios that we'll discuss in a little bit. All the methyl group donors, such as SAM, methionine, choline, then the methyl group metabolites like SAW, homocysteine, which you're probably familiar with, and in general you don't want to see elevated. And then transsulfuration metabolites, the big one there being glutathione. Page 3, just as an overview, is a pathway interpretation. I think one of the nice things that we like to do here at Genova is not just list out biomarkers, but really try to demonstrate what the biomarkers mean in relationship to each other. And so what we did here was we take this methylation pathway that you may or may not be familiar with, but you will be by the end of the hour, hopefully, and place the patient's results right along inside that pathway, so you can get a visual representation of where the abnormals are, where the backups might be, and even the SNP results, so you can have it all combined into one diagram. So there you can see demonstrated where a patient's SNP results would show up on this particular page. Their abnormal biomarkers are going to show up either in the red for standing for outside of the reference range, or in the yellow for borderline. That's also accompanied by sort of a triangle up and down to tell you whether the biomarker was high or low. So again, this allows clinicians to visualize the balance in the abnormals in this particular pathway. And then the rest of the report, pages 4 and on, are dedicated to the genomic results. Each page is represented, each SNP has its own page, and then at the top left of each one of these SNP pages, we have the patient results. So you can see there the gray is indicating wild type or no SNP found, and the blue is indicating that there's a variant found. And then underneath that, you can see it says potential impact, and that will tell you whether this patient's result may result in a potential upregulation or downregulation or neither. Underneath that, we have some more general information about what this particular SNP is that we tested. So for example, here, the COMT, you can see that codes for either val-val or val-met. You might be familiar with that type of nomenclature. And then underneath that at the bottom left, we actually have population categories for the frequency of that SNP, which we don't talk a lot about yet, but the research really seems to be headed this direction, and I think also provides an extra layer of clinical understanding around these SNPs. So for example, in this particular case, in European population, what you see here is that a val-met, or also known as a heterozygous result for COMT, is prevalent in 53% of that population. So it's actually the most common genotype. And I think that gives us a good framework to really start to put into perspective, one, how common these SNPs are, and two, when we're talking about the clinical relevance of an abnormal, what does that mean compared to everyone else? I think these are questions that should be asked, and the research is starting to answer even a little bit more. And then last, on the right-hand side of each page is a fully cited, referenced clinical commentary, so that you can get all the details around what we know about this particular SNP and what you might think from a clinical intervention standpoint. So that's kind of a broad overview. Now, let's get into the details, right? That's kind of what we're here to learn. How do we take the test results and apply it clinically? And one of the first questions that we get asked, and actually when we started educating on this on the phone, some of you calling and asking questions, going over some of your own reports, the question is, where do you start, right? And the answer to that is, well, there's a lot of places you could start, honestly. You could start at the first page with the interpretation at a glance. A lot of good information right at a quick look. I think this is probably going to ultimately be a great overview once you're more familiar with the test. But if you're just learning about methylation and how to use it, might not be the best place to start. Second page gives you a lot of quantitative information. Is it outside the reference range? How far is this biomarker outside the reference range? But ultimately, I think if you're just getting started with this, becoming comfortable, the third page is really the place to start with if you're new to methylation testing. And so that's where I'm going to start. But before I do, we're about to get into some heavy biochemistry. And so I like to take a step back and look at a pretty picture and say, if you truly love nature, you will find beauty everywhere. And that could be in this nice landscape of the mountains, or it could be in a biochemical pathway, right? So with that as our context, when you're looking at this page, the most obvious place to start is with this methylation cycle. This is really what we're evaluating and testing. We're profile is called the methylation panel. So let's start with this methylation cycle. The key takeaway for evaluating the methylation cycle is that methylation at the end of the day is all about making sure that there's adequate SAM, right? This is that molecule that we looked at the very beginning, and this is the one that's responsible for detoxification and ultimately providing that methyl group everywhere that the cell needs it. SAM is overwhelmingly the body's main methyl donor. So I kind of tend to think of it in this idea of like currency. You know, SAM is kind of like the body's cash for methylation. Then SAM donates this methyl group. As you can see, the methyl group coming off, whether that's for DNA synthesis or regulation, whether that's for detoxification, whether that's for producing melatonin or metabolizing different neurotransmitters, SAM donates that methyl group and then becomes SAW, S-adenosyl homocysteine. That's the end product after it's done methylating whatever needs methylation at that time. And then SAW breaks down into homocysteine, and homocysteine is probably a biomarker we're much more familiar with. And I'll take a stop there because one thing to just keep in the back of your head is that homocysteine creates a little bit of a logjam in the system, especially when it starts to become elevated. And I'll show you that in a little bit, but just keep that in mind. So there's a little stop here with homocysteine, and that's why lowering homocysteine is so critically important to the cell. Homocysteine must ultimately be converted back into methionine or mobilized elsewhere. Homocysteine inside the cell is a problem, and the cell has to lower homocysteine by either getting it outside the cell or turning it into something else, or else it'll sort of gum up the entire works of this methylation pathway. And the main way to recycle SAW or homocysteine is to turn it back into methionine. And that's accomplished here by 5-MTHF or activated folate, B12, both of those things are required. But then one thing that's not discussed as much with respect to remethylation and lowering homocysteine is zinc. Zinc is a cofactor for the enzyme that turns homocysteine back into methionine. And you'll hear me say zinc several times because zinc is actually used quite a bit through the entire pathway. And we know clinically how prevalent zinc deficiency, or at least zinc inadequacy, is in our patient population. Now, a little bit on homocysteine. You may know homocysteine is a marker for cardiovascular risk, and there's tons of literature to support that. Elevated levels are associated with atherosclerosis, coronary artery disease, osteopenia, mood disorder, neurodegenerative conditions, right? And you start to realize that that all sounds familiar because those are the same clinical presentations, clinical conditions that are also associated with methylation dysfunction. And that makes sense because a lot of us clinicians not only use homocysteine as a marker for cardiovascular disease risk, but also as an indicator of methylation status, which it should be. Usually clinicians aim for optimal around 10 or 2 to 10, and that's because homocysteine, it needs to be recycled back into methionine to ensure that there's not a backup in this whole system. And here's why. When homocysteine starts to become elevated, it actually can turn back into SAW and cause that enzyme, that AHCY, to favor SAW production. And this doesn't happen at people who have a homocysteine of 15 or 20. This can happen person to person. It can be different. Somebody could have a homocysteine of 8, 9, 10 and still start to produce more and more SAW levels. And the problem there is that SAW actually inhibits all methylation reactions in the body, or at least from everything that I've read, SAW is the main inhibitor of methylation reactions in the body. There's the problem, right? It's homocysteine leading to more SAW. And there's evidence to support that. Here you see plasma SAW is a more sensitive indicator of cardiovascular disease than homocysteine. SAW is a better indicator of vascular disease than homocysteine. And here, the statement, chronic elevation of homocysteine levels result in parallel increase of plasma SAW, which is a more sensitive biomarker of cardiovascular disease than homocysteine. It suggests that SAW is a critical pathological factor in homocysteine-associated disorders. So it sort of flips this whole idea around with homocysteine, and maybe homocysteine is an indirect marker of SAW status. And if you were just to measure SAW, that's going to be your better indicator of both methylation dysfunction and all the clinical conditions associated. So then obviously the next place to go is, we know SAM is the methylation currency, right? It's your body's main methyl donor, and SAW is this indirect or direct marker of methylation dysfunction. So let's compare the two, right? Is it out of whack? And that's why right on the front page, the first ratio we have listed here is the SAM-SAW ratio. You can immediately on the front page get an overall assessment of methylation status. And this SAM-SAW ratio is believed to be a good indicator of cellular methylation capacity, even when you're looking at it in the plasma. There's some good correlates with intracellular SAM-SAW. One thing to keep in mind is that SAM tends to be under more homeostatic control. Why would that be? Well, if SAM is your currency and it's involved in all these different processes, you better bet that your body is trying to make sure that it has enough of it. And if you're starting to run low on cash, you're going to withdraw money from other sources, whether that's choline, whether that's serine or glycine. You're going to want to make sure that you, at least at the end of the day, have some SAM. And so alterations in the SAM-SAW ratio tend to be more due to fluctuations in SAW. And that kind of makes sense, right? Because we already talked about SAW being a really great indicator of methylation dysfunction and cardiovascular disease risk, all those clinical correlations that we associate with methylation problems. Kind of begs the question, why haven't we been measuring SAM and SAW all these years? Well, plasma concentrations of SAM and SAW are 1/500th of homocysteine, right? So it circulates at very, very small levels in the plasma. So you really need specialized technology to accurately measure SAM and SAW, which thankfully nowadays more labs are developing the ability to do so. And I'll also spend a minute here too, because we get a lot of questions around this. SAM and SAW are also very unstable molecules. We have had to be very, very diligent about how the sample is preserved, how it's handled, how it's shipped, including even monitoring the temperature of the kit as it's in transit. So this is something that we have been working very, very hard to ensure that when we receive samples, we have that capacity to ensure that SAM and SAW are accurate and stable. So since we sort of walked around the main methylation pathway, let's apply it clinically. Let's do a case. So we've got 75-year-old female Beth, longstanding pernicious anemia, standard American diet, coffee for breakfast, maybe eat some toast or bacon around lunchtime, or grab some fast food, some processed dinners in the evening, some wine, and clinically has chief complaints of depression, anxiety, osteopenia, fatigue, and osteoarthritis. So let's take a look at Beth's report. And I'll go back to that first question, where to start. Start with the methylation pathway and the methylation biomarkers. And start with SAM-SAW, right? Because these are sort of the big clinical takeaways. So for Beth, we see low SAM, which is our main methyl donor. We see high SAW, which is our marker for cardiovascular risk and poor methylation recycling. And the SAM-SAW ratio, not surprising here, is low, right? Which is a bad thing. That is a pretty straightforward indicator of poor methylation recycling. What's more, you also see homocysteine on the high side. And even the methionine back at the top of that cycle is low. So you're really seeing high levels of those methylation end products and low levels of that methylation precursors, the methionine and SAM. So in this patient, there's an obvious backup in SAW or homocysteine recycling. And since we know the main way to recycle SAM is by turning this homocysteine back into methionine, we'd be thinking about activated folate, activated B12, and zinc. Make sense? So now that we've gone over this sort of main methylation pathway, let's add another layer. This gray arrow is telling you that there's, thankfully, not just one way to reduce homocysteine. The system isn't completely dependent on folate and B12. There's a backup. And the backup pathway is using a molecule called betaine, or trimethylglycine, you're probably familiar, as a different way to methylate, or a different way to turn homocysteine back into methionine. Now, a thing to keep in mind is that this only takes place in the liver, maybe a little bit in the kidneys, but as compared to the main pathway that happens in every cell, this only takes place in those small select tissues, right? So that's why we don't consider this a main pathway. That's why we consider this a backup, because if it were that important, then you would expect it to happen in every cell, where this backup only takes place in the liver. And as I mentioned, trimethylglycine, or betaine, is used as a sort of way to turn homocysteine back into methionine. So where do we get betaine? Well, we can get it from the diet, but we can also create it from dietary choline. So we think about things like meat and eggs and beets to supply this backup pathway. Now, an important takeaway about this backup pathway is that choline is used for other things in the body, right? Choline becomes acetylcholine. It's used in cell membrane repair, and we'll talk a little bit about this. But we don't want to overly shunt choline away just for the purpose of methylation, right? And that sort of gets us back into, well, we still want to support folate and B12 and zinc, because we don't want to be stealing all this choline that's used in other processes just to make up for lost ground with the main methylation pathway. So going back to Beth's results, let's take a look at this backup pathway. And here it is. What do I see? Well, DMG is the first marker actually that I look at when I'm evaluating this backup pathway. And the reason is that the literature has suggested or implied that DMG is actually an independent indicator of BHMT activity, which translates to how much of the backup pathway is being utilized in the system. So here DMG is normal. Beth's betaine is low. Knowing that betaine ultimately comes from choline, and here choline being normal, what is this telling me? A couple things. Despite the fact that there's obvious poor methylation recycling, right? We established that a high homocysteine, a high SAW, a low SAM. This backup pathway doesn't really seem to be filling its job. It's not compensating like it should. So in this particular circumstance, I also would be thinking about betaine as a supplement, trimethylglycine. Another thing on this particular test, under the ratios, you can see they're highlighted number 4, we have this choline ratio. And that's another way that I'll look and see, okay, is the backup pathway working adequately? But there's also some interesting research around the betaine choline ratio. And here I'll go into that just a little bit, because betaine and choline are probably new biomarkers. We're not used to seeing them represented a whole lot. Let's get a little greater understanding about choline and betaine. These two metabolites are quaternary ammonia compounds. Choline is derived from things like eggs, beef, pork liver, soybean, whereas betaine is derived from wheat bran, wheat germ, spinach, and actually beets, which is where it gets its name because it's very high in beets. Choline now is used for, like I said, several different things: acetylcholine production, phospholipids, epigenetic gene regulation, actually, which is kind of interesting. And it's a precursor to all of our lipoproteins like LDL, VLDL, right? So choline is used for a lot of different things, as compared to betaine, which you can see there, primarily used for methylation reactions. So you can see that choline has a lot of responsibilities. Betaine pretty much just used for methylation, which is why I'm saying we don't want to be excessively shunting choline away from all these jobs that it needs to do just because somebody's folate deficient to utilize that backup pathway. Hope that makes sense. Despite its relationship, or I guess in addition to its relationship to the methylation cycle, betaine and choline have independent clinical utility. Choline is a major lipotroph, as I said, responsible for creating VLDL. And there's good literature to indicate that elevated plasma choline is positively associated with pretty much all metabolic syndrome risk factors: high triglycerides, high glucose, BMI, body fat, waist circumference. And this betaine choline ratio, as you can see here, is statistically significant with almost every aspect of metabolic stress. So you can see there at the bottom right, a low plasma betaine choline ratio is associated with higher ALT, higher glucose, higher triglycerides, lower HDL, higher LDL, triglycerides, total cholesterol, and serum homocysteine, right? So not only is there this factor of understanding betaine and choline in relationship to the backup methylation pathway, but if you have a low betaine choline ratio, that's also associated independently with metabolic syndrome, or at least all the factors that we think about when we think about metabolic stress. So pretty great little biomarker on the side. Now that we've talked about the methylation pathway and the methylation backup pathway, let's talk a minute about methylation genomics and how to appropriately apply genomic information. I'll talk about this just for a second because, you know, there's a lot of genetic testing out there. A lot of people have access to their SNP information, and there's a lot of content out there about what to do if somebody has these genetic SNPs. And so, you know, I think it's a nice little, it's a passion point for me is to get people to understand that single nucleotide polymorphisms, these SNPs are very common. Very, very common. Most of us have millions of them. And truth be told, most of these SNPs have absolutely no effect on enzyme activity, which is why we pluck out a few of those millions and study them and do find clinical correlations or at least associations in the literature. These SNPs may alter the activity in a way that speeds up the enzyme or slows down the enzyme, and that's upregulation versus downregulation. And last, genes do not make your destiny. I can't say that passionately enough because, you know, sometimes we will hear these examples of clinicians calling in or patients calling in frantic about the genetic SNPs, frantic about MTHFR or COMT. And my follow-up question is always, well, what's their homocysteine level? And if the answer is, well, it's normal, then why are we worrying, right? I would tell the patient, good job compensating for the genetics, because genetics are just predisposition, right? It's the phenotypic markers like homocysteine that are going to tell me what's happening right now and whether I'm going to change my clinical intervention right now, right? I hope that makes sense as well. That being said, on the methylation panel, we're looking at 10 SNPs and remembering that first, which ones upregulate and which ones downregulate. That's really going to help. And so I tend to remember it this way. There's three big main methylation SNPs in the middle: MTR, BHMT, and GNMT. All three of those guys result in an upregulation, meaning if the patient result comes back with a positive, or especially two positives, then that's going to make that enzyme work faster. All the rest of these result in a downregulation, or those enzymes work more slowly when there are positives there. So starting with these three that result in upregulation, let's just talk about them briefly. MTR is actually the enzyme that results in turning homocysteine back into methionine. And as we mentioned, this SNPs here make that enzyme work faster, which actually results in homocysteine coming down and making more methionine, which kind of sounds like a good thing, and it might actually be in certain populations. The downside of that is, you know, folate is not just used for methylation. It's used in DNA synthesis, purine synthesis, a lot of different things. So like everything, there's a balance. And when there's a SNP here for MTR, it might actually offset the folate cycle, which is an entirely different webinar, but just something to keep in mind. Apologies. BHMT in the middle here is that enzyme responsible for the backup pathway. And if there's SNPs here, the patient has a tendency to make or to utilize that backup pathway more often, which you can see here is kind of fitting with that clinical picture with a lower methionine and a higher homocysteine, because the patient is negative for this BHMT, meaning that that enzyme may work slower compared to some other individuals. And then the third one, GNMT, we haven't talked about yet, but GNMT is this side pathway that actually is responsible for disposing excess SAM. It actually takes SAM and kind of gets rid of that methyl group without, you know, methylating DNA or making epinephrine or detoxification. It's kind of an excess disposal chute. And SNPs here will actually result in proportionally more disposal of SAM, which you can also see, right? SAM is on the low side and SAW is on the higher side. And whether that SNP is playing a role, I think is a, you know, it's a really interesting point here. So from there, the rest of these, as I said, result in a down regulation. First and foremost, MTHFR, which we probably know the most about, or at least we talk the most about when it comes to methylation pathway genomics. And this results in a reduced conversion of dietary folates into this active folate, which is the 5-MTHF, right? So you consume dietary folates in broccolis, green leafy vegetables, things like that. It has to be activated by the system, and that's really MTHFR's job. So if you have a bunch of SNPs here for MTHFR, this patient has a higher likelihood of making less active folate. And clinically, that's where you might consider reaching for your actual 5-MTHF as a supplement. Now, MTRR is an enzyme that keeps B12 working properly. And there's a lot of literature actually on this MTRR, and if you have SNPs here, it results in a predisposition towards repair of B12. And the way this works is, as you can see there, B12, there's sort of a red B12 and a green B12. The more that the system utilizes B12 just in its regular, going throughout the day, the more that B12 gets used, the more susceptible it is to oxidative stress. Once B12 is oxidized, it's not usable anymore. And this enzyme, MTRR, actually repairs it so that it can be used again. So SNPs here clinically, I might be thinking about, does this patient need more active B12, methyl B12? And then the last one we haven't talked about is MAT1A, which is the enzyme that actually turns methionine into SAM. And SNPs here result in a downregulation, meaning there's a harder time for the methionine to turn into SAM. Now, whether this translates to perhaps short-term use of SAMe supplementation, you might want to use your clinical judgment around that. So looking at the case thus far and what to consider from a therapeutic standpoint, folate, particularly 5-MTHF, makes a lot of sense here given the high homocysteine, the SNPs, and the low methionine. B12, especially methylcobalamin in this particular case, and then betaine to support that backup pathway. Because as we mentioned, whether it's the SNP or just the system in general or lack of cofactors, we might want to support that backup pathway in the short term, because that doesn't seem to be compensating very well. And then again, that question around SAMe supplementation. What about glycine? We'll talk a little bit about that. Now, going back to the front page, we mentioned there at the bottom here, we have these ratios for methylation status. The first one, the SAM-SAW ratio that we talked about. But what about the second one, this methylation balance? Well, what we did here was, since we know and we've got how the body tries to keep SAM pretty stable, the body actually tries to keep SAM and SAW pretty stable so that it's not, errantly altering DNA with epigenetics or, having problems with detoxification. The body tries to keep SAM and SAW pretty stable. And we saw that there's ways that the body compensates. There's a backup pathway, and there's a main pathway, and there's actually other ways that the body can try to compensate too. So the question becomes, can we see dysfunction or imbalance in the system before SAM and SAW are altered? And that's kind of what we're going at with question number one for the methylation balance. The other thing that we're looking at here is, can we see in the system when there is too many methyl groups, when there's a propensity or a risk for over-methylation? That's kind of the concept. And what we did was, we take 4 biomarkers that have a methyl group to give, and we simply compare that to 4 biomarkers that have had a methyl group removed. Right, so thereby we're saying we're not just looking at SAM and SAW, we're not just looking at homocysteine, we're looking at the whole system and saying, is there an imbalance between the number of methyl groups compared to the analytes without a methyl group? This is a novel assessment for methylation status, and we're currently undergoing research and compiling a lot of information around that. One other thing that wasn't mentioned thus far was serine and glycine are also on this test. And what do we do with those? Well, glycine and serine are very, very basic amino acids. Glycine alone is used in 3 different pathways just on this report, and it's used in numerous pathways. So they can be a little bit tricky. However, clinically, I think glycine is really great to look at as it's a need for pre-glutathione. Glycine is one of those 3 amino acids that's used for glutathione support. And it's also needed as this SAM disposal. So for instance, if you had a patient result that came back with a high SAM, I certainly would be looking at glycine in that circumstance as well, which does happen. Serine on this particular report is also involved in a lot of different pathways. And, clinically, I don't use that as much as an independent or biomarker indicative of a clinical need all by itself. It's really used primarily as a calculation in that methylation balance ratio that we just talked about. So now that we've kind of gone over the main methylation pathway and how to use it, let's do another case just to kind of get a little bit more familiarity. 55-year-old male, George, 10-year history of obesity, who began a paleo diet for weight loss and is doing very well. High meat intake, not particular about the quality of meat, just, very high meat intake, low complex carbohydrates. So what are you thinking about there, right? I'm thinking about maybe low folate intake. Has been exercising, mostly anaerobic, and a family history of cardiovascular disease and alcoholism. Let's look at George's report. See a high SAM, high methionine, high homocysteine, high choline, serine, glycine. And when you think about his diet, that kind of makes sense, right? He's got a very high protein intake. So you would expect a higher choline, a higher serine, a higher glycine, higher methionine, just due to all that protein intake. But another thing to know is that higher levels of SAM correlate a lot with people who are overweight and obesity. Not only that, you can see his SAM-SAW ratio is toward the higher end. Methylation balance, though, is actually toward the middle. So when you compare his methylation balance to the SAM-SAW ratio, this might be telling me that this is an individual who might be having a higher SAM simply because of either that high protein intake or being the fact that he's overweight or obese, or maybe both. And the literature does support that, actually. Some more literature, or recent literature coming out to suggest that over-methylation might be a signature of high BMI, high protein intake, high caloric intake, and people who are overweight or obese. And so when you see higher levels of SAM, that may not always be a good thing. And the first thing to evaluate is metabolic syndrome. And it also, from a more, philosophical question is, should we start to reconsider metabolic syndrome as an over-methylation condition? And there's some literature here you can see to actually support that. Last, we mentioned over-methylation. Is it a thing? I'm not going to go into this too much, but clinically we do have a lot of feedback, and we do see a lot of patients that when taking too much folate, they start to show these signs and symptoms. And the main theory there is that with higher folate intake, you might be pushing the methylation pathway to make more SAM, which could ultimately result in more epinephrine production, or at least altering neurotransmitter metabolism. Unfortunately, this isn't something that's really been studied in the literature, but it is something that we do tend to talk about and see clinically. And is there a way to look at that on this particular test? I would say looking for a low homocysteine, but then a high SAM-SAW ratio would be the big things to think about. And since we have that methylation balance ratio, also another thing I'd be looking at. Some common clinical interventions are things like niacin, glycine, as I mentioned, because glycine is that precursor to SAM disposal, right? It kind of removes excess SAM. So I think that makes a lot of sense clinically if we're dealing with somebody who's reacting poorly to either SAMe or to methylation support. And finally, vitamin B6, because vitamin B6 can then create another offshoot to this whole system. So going back to George, what are some of the therapeutic considerations? Certainly ensuring adequate dietary B vitamins. I would think especially B12, given that he has a high homocysteine. Remember zinc, right? You see here that zinc is a cofactor for the main methylation pathway, but it's also a cofactor for the backup methylation pathway. And what we're seeing here with George in that backup pathway, the BHMT, higher homocysteine, higher methionine, and he has a homozygous positive SNP for that, meaning that BHMT has a propensity to work fast. So we want to make sure that there's adequate zinc to assist in that. What about protein reduction? Well, I think, again, this is another sort of question that, if it's clinically appropriate or your particular evaluation of the clinical case seems to be working fairly well given his weight loss. And as long as I'm supporting betaine so that this betaine choline ratio is not on the low side, then, it might not be something that I'm talking about right away. I think we have enough to work on. Let's take a look at one more. Here we see a high homocysteine, borderline high SAW, but SAM and methionine actually look good, right? So what do you do in this case? Well, I mentioned that homocysteine creates a logjam in the system, right? It leads to higher SAW levels. So another thing to think about, if you have a high homocysteine, but a lot of the other biomarkers look good, let's try and get that out of the system. And that leads us to transsulfuration. That leads us to this bottom part of the report where homocysteine can leave the cell and become ultimately either glutathione, pyruvate, and taurine. So since you're all experts on the methylation side of things now, let's briefly talk about moving to the transsulfuration side of things. And the main outputs, the main things we get out of transsulfuration are down here. The glutathione, which is one of the body's most powerful antioxidants, pyruvate, which then enters the Krebs cycle and becomes cellular energy, turns into ATP, and then taurine, which has a lot of uses in the body. So key takeaway regarding transsulfuration is this. Transsulfuration is upregulated by two critical factors. The first one is SAM. SAM actually allows CBS to work properly, right? So CBS is the enzyme that turns homocysteine down into the transsulfuration pathway, but it requires SAM. SAM is an activator of that enzyme. So if you have higher SAM levels, you have more transsulfuration. If you have lower SAM levels, you have lower transsulfuration. That's a critical takeaway. And oxidative stress, which makes sense. If oxidative stress is present, then the body wants to make glutathione to take care of it. And so there's a feed-forward mechanism that says, hey, there's oxidative stress, make more glutathione, and that shunts things down this transsulfuration pathway. Two really, really good takeaways. So given that SAM availability determines the rate of homocysteine transsulfuration, what does that mean? It means that glutathione production will not take priority over creating SAM, meaning that if you have a low SAM, you have a high risk of having low glutathione. So a lot of times clinically we evaluate glutathione and you're like, oh, I'm giving glutathione and it's not getting better, it's not getting better. Well, have you looked at methylation? Because to produce glutathione, you need SAM. And that gives us a whole greater understanding of how these two pathways interconnect. When you look at the report on the front page, if I see a lot of biomarkers showing up there, I would be thinking about transsulfuration. And certainly if this met-sulf balance is favoring methylation, I'm thinking about transsulfuration. And why is that? What we did with the met-sulf balance is we simply said, let's take the biomarkers from the methylation pathway and compare them to the 4 key biomarkers of the glutathione pathway. That way we can get a top-down look. Is there an imbalance between these two pathways? Because as I just mentioned, transsulfuration is dependent on adequate methylation. And if there's a backup here, maybe it's somebody having a low glutathione because they've got a backup in between these two pathways. And there's something different that you would clinically use. You would use things like B6. You would certainly support the methylation pathway, but B6 is the main vitamin for transsulfuration. Also magnesium and zinc, but B6 is the big one that I think about there. So for this last case, putting it all together, SAM-SALT ratios actually look okay, but the homocysteine was still high. But here's our clue. The methylation is being favored over the transsulfuration, right? It's because we want to ultimately and ideally have all those ratios a little bit toward the middle. Unless you have some reason to push a particular pathway, maybe you really want this person to have more glutathione. It makes sense clinically, you want to push a pathway, but in general, we want to have these ratios toward the middle. I'm going to skip this in the interest of time, but I think this is important just to kind of take a step back and kind of discuss where to start and what we went over. So with this third case, so you don't get overwhelmed, what's the best place to start? And I would say always start with the analytes that are most clinically significant, right? So number one, what is the SAM, what is the SAW, and what is the SAM-SALT ratio? You know, that's going to tell you the broadest information about methylation status, whether it's adequate or inadequate. Then try to determine where the backup is. In this particular circumstance, you can see the patient has a high SAW, but their homocysteine is normal. Well, look, there's a cofactor right there, B3, that turns SAW into homocysteine, right? So you find the abnormals, especially the most clinically significant, then look to see where the backup is. Next, it's good to look at the choline and betaine balance, because as we mentioned, not only is this a backup pathway for methylation, but it's also associated with metabolic stress. So how is that looking? Do I need to support with trimethylglycine or betaine or choline? Then, what's the glutathione production and transsulfuration activity? And if there's a problem there, where's the backup? Like for instance, you see here a high glycine and cysteine, but low glutathione. Cofactors needed there are things like zinc, again, and magnesium. Next, look at these more delicate ratios. What's the balance? What's the methylation balance ratio? What's contributing to that? So in this particular circumstance, you can see the methylation balance is a little bit on the lower side, most likely because of SAW being on the higher side. SAW is part of that calculation, and that's probably what's driving that to be on the lower side. And then lastly, I think the genomics are good to evaluate, because that tells you about where the trouble spots might be. Not only does it help you understand and fit everything together as far as why this patient might be where they're at with their methylation cycle given their diet. You know, maybe they have a great diet, but they're still seeing some trouble spots. Why might that be, and what should we focus in on a little bit more? Also, maybe their biomarkers look fairly normal, but it gives me an idea of, from a multivitamin standpoint or from a prevention standpoint, where do they have more risk? Do they have more risk with activating folate? Do they have more risk with this backup pathway? And that can tailor my intervention even more on a personal level. So for instance here, you can see that there's MTHFR SNPs, which might be a concern down the road, but we're not seeing homocysteine elevation yet. Maybe that's because this MTR upregulation is happening. Maybe that's lowering homocysteine and leading to higher methionine. You can see the BHMT also an upregulation, which would tend to lower homocysteine and lead to more methionine. And then ultimately, the GNMT SNP might be removing more SAM, leading to higher SAW production, right? So it all makes sense with the clinical picture here. And now you can see on one page how the genes are interacting with the biomarkers and how it's all coming together. So just with a few minutes, I'm gonna really briefly go over some of the things from a treatment standpoint, right? So we've got those three pillars on the front. We've got the methylation pillar and the transsulfuration pillar. You'll have these slides available to you if you wanna go back and look at these. But when I see a lot of problems in the methylation pillar, I think about methylation support, like green leafy vegetables. Transsulfuration, I think about vitamin B6, magnesium, glutathione. When it comes to folate, there's a lot of discussion out there. Obviously, we're strongly emphasizing folate-rich foods, but there are people who have pretty significant MTHFR SNPs that might make us worry about, are they activating that dietary folate? And when it comes to folic acid versus folinic acid versus 5-MTHF, probably a whole webinar in there as well. But there is a lot of debate. Folic acid has been vilified quite a bit. And honestly, I think the jury is still out on whether that is whether that should be the case or not. We know that folic acid does have some concerns around competing with the folate receptors in the system, but we also are seeing evidence that what that really ends up as causing a problem or not, that hasn't been demonstrated. As compared to 5-MTHF, one of the concerns is that that irreversibly commits folate, or this form of folate, to the methylation cycle. It's not something that can go back and turn into our dietary folates to be used for other systems. So, maybe at the end of the day, we'll see that folinic acid is the best form to use. But I still think there's some work to be done here when deciding which is the best one to use. And that's why the results will help you determine which is more appropriate for that patient. Vitamin B12 deficiency, very common, pretty familiar with the dietary sources. And serum B12, just keep in mind, may not tell you the whole story when it comes to vitamin B12 deficiency. That's where we might reach for things like methylmalonic acid on an organic acid test, like on the NutrEval or the Organics. Vitamin B6, particularly useful if there's poor transsulfuration or poor glutathione production. There's two different forms. There's the P5P and the pyridoxine. There is some question mark around how well P5P is absorbed, but we also know it's more bioavailable. So it might be a bit of a trade-off between the two. Zinc is a very common mineral deficiency, not only used for the main methylation pathway, but also used for the backup pathway and used for transsulfuration and glutathione production. So again, I can't emphasize evaluation of zinc enough. And a great way to do that is to look at something like a plasma zinc copper ratio, which is also available on the NutriVal. Choline and betaine not only have been associated with metabolic stress, but as a treatment have been shown to demonstrate a lot of improvements from a lipid standpoint, reducing NASH. So just from a supplement standpoint or a dietary standpoint, this is really great. And soy lecithin is pretty cheap, pretty easy to introduce. Glycine has been used for anxiety, poor detoxification, and with respects to methylation, it actually improves overall methylation balance, has been shown to do that, and it's a precursor to glutathione. So another great supplement to be using for methylation treatment and evaluation. Last thing here is SAMe, which has been extensively researched in many conditions. I do think that we tend to see some people not react to SAMe very well. Particular concerns are in bipolar and schizophrenia, but there are some people that seem to get a little edgy, a little jittery, and the question is that because SAMe is causing COMT activity leading to more epinephrine production, which makes sense when you look at the biochemistry. So with that, I know that was a ton of information. I didn't leave a lot of time, but we do have a lot of support materials available on our website. We have the methylation pathway for you to study and love. We have the methylation panel support guide. We have another video that will walk into the details of methylation overall sample reports. And certainly give us a call with your clinical consultations, questions to discuss with me and my team here. And yeah, I just appreciate your time and attention. Take it away, Lenore.
Amazing presentation, great information. I do want to remind folks, number one, as Dr. Chapman mentioned, that available on our website, you can download the support guide, which is referenced, and it has a lot of additional details and information. The next thing is that, again, the presentation, the slide deck will be available within a few days after the webinar, and you'll be able to access the resources and re-listen to this wonderful webinar as well as other webinars that we have available on the website. So let's go ahead and I'm going to try to hit the most common asked clinical questions, okay? The first one is, in an ideal world, we would love to order the methylation panel for everybody, but is there a particular patient population that you feel benefit the most from this panel?
That's a great question, and honestly, kind of a hard question to answer. You know, we think about cardiovascular disease, we think about cancer risk, family history of cancer risk. Those are kind of the big ones. But, you know, some of the other ones where it might uncover something we haven't already are things like cognitive decline. There's a lot of information connecting methylation dysfunction and cognitive decline, and it's not always the first thing we think about, right? Another is, you know, maybe behavioral disorders, either mood disorders or things like ADD, ADHD. This could be, there's some good literature out there as well connecting the methylation status and those clinical conditions, you know. So, you know, if we're talking about from a broad perspective, yeah, it'd be great to run it on everybody, but those particular cases where maybe it's underneath and we haven't thought about it, that's a perfect patient population to be thinking about this test.
The other most common question we received is, do patients have to discontinue supplements prior to sample collection for the methylation panel? And if so, for how long?
Patients aren't required to discontinue things like B vitamin supplementation. You know, there's kind of two approaches. Do I want to take this patient off of their supplements to see what their baseline status is for methylation? You know, I think there's some clinical value there. Or do I expect to continue B vitamin supplementation on this particular patient and want to know, is it enough? Or do I back off, or do I change it somehow? You know, I think under that circumstance, you can also run the test and not discontinue the B vitamins. With respect to SAMe, that's probably going to show up as CME, or if somebody's taking choline or trimethylglycine, we're evaluating those biomarkers. So I would expect to see that in the test. So, maybe those would be something to consider discontinuing. You don't have to, but if you find a huge elevation, it's probably because they're taking it.
What about a patient who has an elevation in homocysteine and SAW? What would we consider to help lower those markers if they both are elevated?
Yeah, that's a great question, and I think ultimately is kind of gets to why do a test that has so many different biomarkers, right? Because from homocysteine, there's 3 different branch points. It either goes around the main pathway to make methionine, it goes around the backup pathway to make methionine, or it comes down into transsulfuration. So I hate to answer a question with a question, but my thought would be, well, where is it not going? Are we seeing backups in that main pathway? Is the backup pathway not working? Or is it not coming down into transsulfuration? And that's what that met-sulf balance ratio can tell you, and that's what that methylation status ratio can tell you, and as well as things like DMG that evaluate the backup pathway. So if you're just kind of painting with a broad brush, you could be giving a lot of the different methylation treatments that could, at the end of the day, add up. But is it really the area, the weakness? And I think that's what makes this test really great, is it can tell you the differences between your clinical interventions and whether you're targeting the right spot.
In the interest of time, we're going to end our question and answer period there. For additional education materials, we'd like to encourage you all to visit our website, where you can download not only the support guide for the methylation panel, but also learn more information about collection and the different biomarkers as well. We also offer complimentary appointments with our medical education specialists to answer questions related to our testing, including how do I choose the right test and reviewing patient test results. We'd like to encourage you to register for the upcoming webinars on our website, www.gdx.net. Next month, we will have Dr. Kara Fitzgerald speaking on lifestyle medicine and the methylome, and several dynamic speakers and topics to follow in the upcoming months. Dr. Chapman, that was an amazing presentation. You've received so much positive feedback, and we really thank you for your time and energy that you spent reviewing this topic with us.
Thank you very much. Have a great day.
Will do. Goodbye.